While probability theory is properly considered an area of pure mathematics, statistics and statistical inference lies more within the realm of science in that it aims to investigate experimental data. What do I mean by that? Well, statistics actually sits on top of probability theory and uses many of its concepts, including but not limited to those of random variables and probability distributions. Whenever someone performs an experiment and takes repeated measurements, one doesn't expect to measure the same thing every time. And in that way, it's a good situation to model in terms of random variables and probability distributions. So supposing we've identified the form of a probability distribution, then statistical inference is a set of tools and heuristics for learning information about the underlying probability distribution. Now, that might seem like a lot, but we're going to take some time to carefully identify and describe any language that we've just used and that we'll use going forward. And the first piece of language, the first concept, is that of an experiment. So what is an experiment? Well, an experiment consists of n, where n is a number, n measurements of a quantity, and that quantity we'll call it x. And what does that look like? Well, typically we're going to write it as capital X, a vector capital X. We'll see why it's capital X in a moment, but it's a vector containing the objects x1, x2, dot, 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 xn. So if we just box that up, we call these the data items, resulting from an experiment. And now to address why in particular this x is capital. Well, x is a random variable, just like we discussed before. When you perform an experiment, you don't necessarily expect to get exactly the same results each time. And in that way, it's a good candidate for modeling in terms of random variables. So the data items x are random variables. They are random variables. Now, to complete the description of a random variable, one must state what probability distribution they follow. And that probability distribution in the context of statistics has a name. It's called the population. So the population. What do we mean by the population? Well, the population is the probability distribution, and we're going to give it a name. It's P capital X of lowercase x, and we'll have more to say about the capitalization in just a moment, but it's a probability the probability distribution followed by the data items x, capital X vector. Moreover, it is a joint probability distribution, meaning that it's one probability distribution for all of these random variables x1 through xn. Okay, and we can be a bit more explicit about what we mean here. So really, this is a continuous process. So we think of these random variables usually as continuous. Not always the case, but most of the time it will be. So we're going to write that the probability that capital X is equal to lowercase x is equal to p x lowercase x, but we're going to multiply it by a volume element. So it's dx1, dx2, dot, 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 all the way up to dxn. So what's happened here is we are multiplying all the dxi's together to represent that really what this is a density. Okay, so this is a volume element which makes this px of x a probability density. So this is the population is, if you like, properly the probability density function for the random variables or the data items. So it's a PDF, a probability density function. Okay. Now let's get these definitions boxed up as well. Beautiful. So it's worth talking about this lowercase x. So let's just be a bit careful about the difference between lowercase x and capital X. Well, as is exactly in the same way as we talked about with probability theory, the capital X's are random variables, but the lowercase x's are samples. Okay, so let's make another definition. The samples and these are particular values, lowercase x, that the data items resulting from an experiment may take. Okay, so these we call them samples. Okay, and it's also worth noting that when we make a measurement, we say we have sampled the n-dimensional population. And what is the n-dimensional population? It is just our good friend px of x. Okay. Now that we have a bit of language, it might be worth just talking ourselves through an example. So let's say example. Well, let's say let x, so the quantity x, be the average temperature in Paisley. Average temperature in Paisley. So, and then we'll say our experiment consists of making, let's say, five measurements of this temperature X. Okay. So what do we mean by that? Well, we have X1, we have X2, we have X3, we have X4, and we have X5. And these, remember, are random variables, so they can take any value, but of course the frequencies of each particular value will depend on the probability distribution. But we'll say X, capital X1 is equal to lowercase x1, which could be, let's say, I don't know, 14.3 degrees Celsius. And we'll have X2, and we'll say that's equal to, let's say, 15.1 degrees Celsius. We'll say X3, let's say it's closer to midday, so let's say it's, I don't know, 17.5 degrees Celsius. And we'll say X4, let's say it's, for one reason or another, gets a bit hotter, 18.0 degrees Celsius. And finally, let's say we took one measurement a bit later on, and we got, let's say, 13.7 degrees Celsius. Now, the capital Xi, these capital Xi, these are our data items. Right? And it's important to note, remember, these are random variables. Okay? And these lowercase xi, these are our samples. These are our samples. So these are particular values we measured for our random variables. Okay? And our population, well, we don't know what the form is, but it's some probability distribution that we've drawn these from. So we'll say the samples are drawn from the population. Okay. Now, thus far we've been discussing a fairly general case. That is, all of our random variables, the distribution could be any horrible function we like. In particular, it could be the case that one measurement affects the next measurement, but usually the situation is a bit simpler than that. So usually experiments are simpler. And they're simpler in two ways, because usually the data items have independent distributions. Independent distribution. So what that means is the resulting distribution function will be a product. And in addition, the measure, well, let's just talk about this for a second. So if they have independent distributions, what we really mean by that is that one measurement cannot affect another. Okay. And in addition, the measurement, let's say the data items further have identical distributions. And again, loosely speaking, what this means is that the measurement procedure does not change between samples or between data items, we'll say, between individual data items. Okay. And together we have a way of describing this condition. We say we have independent, identically distributed random variables. Or another way of saying that is we say we have IIDs. Okay, it's language we might find ourselves using sometimes, but it is also very, very common to talk about this situation. We say that the data items, the x1, the x2, all the way to xn, we say they are IIDs. Okay. Okay. Very good. So, I mean, this situation, again, we say we've simplified it by quite a bit. It also allows us to use one more piece of language, and we say, in this case, we say, when we've performed an experiment, we have taken n, let's say, n samples from the one-dimensional population. And what's the one-dimensional population's form going to be? It's going to be P of X. And just to be explicit about what we mean here, essentially what we're saying is if we have IIDs, so independent, identically distributed data items, we say P X of X takes a lovely simple form. It's P of x1 times P of x2 dot 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 times P of xn. So the independence is the fact that our function of n variables is a product of functions of each of one variable, and the identically distributed is the fact that each of the functions around the x's, they're all the same function p. Okay, so let's again just box that